that we've already discussed. The structure of this talk is similar, so I want to motivate the problem, review current best practices, discuss methods that are currently used, and then analyze our result that we've obtained and give an outlook for future research. So, like anybody who's concerned with energy modeling will soon discover that there's a lot of packages available, a lot of code available generally with different features, different focuses, but the problem is that the interoperability of those solutions is very poor. So taking an example like this, somebody published some detailed data set that he spent a lot of time on composing on mainland Europe, for example, on the transmission system. And in another package, I have a great power flow algorithm, and the question is usually, okay, like, can I use this algorithm to conduct a case study on the specific case that I found? And the answer is always yes, but it's difficult because it requires a lot of manual labor, because you have to make sure that the data that is provided by the researcher that created the test case is in line with the data that is expected, for example, by the algorithm that you want to use. And a couple of great test cases are PSA, for example, or RE Europe, which I'm using in the experiments that I'm presenting in this work. And the advantage that a standardized data format would have is that re-implementation of functionality would be minimal. That's often required nowadays. Then accessibility would be higher, because even if somebody spent 2 years of their PhD making a very detailed data set and nobody's able to easily use it, it's sad. And then validity of results can also be checked more easily if everything is interoperable. So I said previously there's no standardized data format. Of course, that's not the case at all. There are definitely solutions currently available, and one of the most popular, I would say, is pglib, which is a library for power flow simulations. And the data structure that is used there is also adopted by MEDPOWER, which is very popular, and then power models as well, even though they make slight adjustments to that model. The shortcomings are that these structures don't consider time series data, they don't tell you how to deal with your results, and then geographical data for case studies, for example, is also not considered. But the data format would be a great foundation for a standardized data format. So what we've done in the scope of the study is to really look at the data that is required by researchers and classify it as according to this figure. So we have some core data which would be required to run a power flow simulation, and then we would have additional data like auxiliary data, which could comprise geographical information, scenario data, which could include time series, and then results like power flows, reactive, active, stuff like this. And the standardized data format that we've developed and used is basically comprised of the core data, which would be our pglib tables, which tell us what properties our lines, generators, and buses have. Then we would have auxiliary data, as I've explained, including geographic coordinates and so forth. So, and to then like really test and to then really like conduct research on this kind of field, we've developed a Julia power flow algorithms and a web server to which we can upload our power flow simulation results and then plot them using OpenStreetMap. And the question here would really be like, if one would define a standard format, how would you do it? And I think the best way always would be to have some standardized intermediary format that can be like read and exported to by all solutions like we have in mathematical optimization, like problem formats that every solver supports, for example. And then finally the analysis. I've just solved 2 problems using this test case data, uploaded and visualized the results using our web service and OpenStreetMap. And what you can see in the top left is just the general network structure. At the top right, you can see locational and marginal prices. Then I also ran a clustering algorithm for those prices. And as you can see, Malta and Italy, for example, have very similar electricity prices. I don't know if that's surprising, probably not. And then what else? Operational switching statuses I also plotted. So I think there's a lot of potential, and yeah, it's just something that I had to deal with. Thank you for your attention. That's it.